Good morning, everyone, and thank you for joining today's new product update webinar session. Today, Uwe Fuhrmann will be speaking on EMI optimized buck converters for core supply and point of load. We have systems engineer Omar Higazi standing by to help answer any questions. So we welcome you to ask questions using the Q&A box on the left-hand side of the page. You can also view additional resources related to today's topic on the right-hand side, including product folders and evaluation modules. All right, I hope you enjoyed today's session. I will now pass it over to Uwe for introductions.
Thank you very much. Yes, let's talk about buck converters for core supply or point of load that are specifically developed to be EMI optimized. My name is Uwe Fuhrmann, Product Marketing for DC-DC converters. And when we briefly look at the agenda of today, you will learn how a specific developed on-chip integrated capacitor can help you to optimize the EMI performance of the new step-down buck converter DC-DC. And that can, of course, help you to facilitate the CISPR system compliance. So we will look at some of the EMI measurements that we have done with this new TPS 628303 buck converter family. We will also look on some of the transient response measurement that we have done. As you might know that specifically the digital system on chips, the FPGA or MCU, they typically ask for very fast transient response to cover a good system performance. And last but not least, very shortly, we will look at an option that is possible with this new family here that we call dual layout. And that can help you on supply security and best availability of this new product. As said before, please feel free to chat with Omar, our systems engineering manager, who is available to answer your questions throughout the presentation. Now, when we talk about buck and step-down DC-DC converters, we see basically three major trends that our development teams are looking at when they do a new product family. One of them is the so-called power density, which means very high efficiency at small size. And when you're developing a new system, you very often have been asked to either reduce the size of the board or maybe to add additional functionality to the same size. That means power density is getting more and more critical in many applications here. And when we talk about power density, we distinguish between two kinds of power supply rails, which one is a core supply for the embedded processing, the FPGA, etc., which very often have requirement for fast transient response, very tight accuracy, etc. And on the other hand side, the point of load, where you may have 2, 3, 4, 5 or more rails on your system that you also need to power. There maybe the very small size is critical, but also a family concept may help here, because if you have multiple power rails on a system, then it may make your life a little bit easy if you have a family concept for the buck converters where you can exchange very easily without changing the layout from a 1 amp to a 2 amp or from a 4 amp to a 3 amp buck converter. A little bit a different topic is a low noise trend that specifically is important for the analog circuitry, for the signal chain, precision signal chain, maybe for the sensing, but of course also for audio and any kind of wireless connectivity. Here often the buck converter, the DC-DC converter is required to either work in a forced PWM mode to give you the very low output ripple, also at light load conditions, or even having a fixed frequency with a synchronization capability that you can then easily filter out this one switching frequency if you have multiple buck converter on a system. And of course, for these analog sensing applications, you sometimes need also a negative supply to power an operation amplifier or a data converter. And last but not least, for battery-powered operation, some of the buck converters have a specific feature that is called the ultra-low quiescent current, together with the very high light load efficiency, just to extend the long battery runtime in your system. But today we will specifically look at the power density. And because there are these kind of different requirements depending on the load and the system requirements, of course the portfolio here we can show you just as a brief overview. Some of these are specifically made for very high efficiency. Some of them are made for the fixed frequency that I mentioned that you can synchronize. Some of them are made specifically for the smallest possible size, and then of course some of your systems just need a good enough buck converter, so these are cost optimized. Some of them have a dual channel, and some of them made for battery runtime. This is just a very brief overview of different output currents. So when we say 1 amp, 2 amp, 3 amp, that means maximum output current. The family concept I mentioned before is what we mean here when we, for example, have a 1 amp, a 2 amp, a 3 amp, and a 4 amp with the same pinout. So you can exchange on the same layout basically from 1 to 4 and sometimes up to 6 amp with the same pinout. That can on one hand side make your life easy because you do not have to change your board layout if you, for example, within the development time of your system see that maybe you need a little bit more power. You thought 2 amp is enough, but at the end you say, well, 2.5 is better here. So you could just, without changing the layout, the board, just use another one of the family concept. However, one important parameter is missing here, and that is the EMI compliance. And this is unfortunately very often an afterthought. In many of the systems that are developed, the design engineer is looking to get the functionality correct, parameters, performance, efficiency, etc. And then at the end, when the board is basically ready, well, it needs to be tested, maybe even certified to some standards and maybe given out to an external company for this certification. And then you may have a surprise if it fails or not. And then you start to, troubleshoot, search and do another iteration, maybe a third iteration till you get the certification and the EMI compliance. So when we talk about EMI, well, this is electromagnetic energy produced as an undesirable byproduct of the switching current and voltages. So that comes from a variety of physical phenomena, and during these, and then you see it only during the EMI test. And of course, you also know that there are many methods described in books, and you will find a lot of help on the web, also on TI.com, how to reduce EMI. However, the problem very often is that these are plugged with trade-offs, and this can be, for example, you need to add additional components, maybe expensive filters, or you may need to reduce the switching slew rates, etc., etc. And all these conventional methods may have some trade-offs that can impact efficiency or functionality. So today we would like to show you here some innovation that to realize all the benefits of a switching power supply, but with an EMI reduction technique to resolve all these trade-offs. And here we have now introduced the new TPS 62803 family of buck switching regulators. So let's have a look at what this family is. As I said, it's a family, so you have 1 amp, 2 amp, 3 amp, 4 amp pin-to-pin compatible. And this family here has on-chip, so on the silicon, noise filtering capacitors, and specifically at the inputs of these buck converters. And this on-chip noise filtering capacitors, of course, can help you really to improve the EMI performance compared to previous generation by a good factor. and maybe then can help you to have a compliance to the CISPA test. The good thing here, we have also improved the input voltage range, the output voltage range, so you can go, for example, down to 2.25 volt at the input, and that can support, for example, a few of the new memory standards where we have seen that these are going down to even below 2.3 volt at the input. We have a fairly good power switch integrated with low RDS on, and from the output voltage we are here going down to 0.5 volt. As an example, this can of course power some of your digital ASICs or so, but it can also power the new memory standard LPDDR5 that is specified to 0.5 volt at one of the rails. Then we have of course the high accuracy of 1% feedback voltage accuracy to support the core voltage requirements of many of the FPGAs or processors. Important here is probably that in the data sheet, this 1% feedback voltage accuracy is specified over the full input voltage range as well as the full temperature. And this is, as you might know, not the case for all buck converters that you can find on the web. But this one here, this family, is similar to many of our newer parts, have the very good accuracy over the full temperature range. Very low quiescent current in case you're working from a battery, and you can switch between a so-called power safe mode or pulsed frequency mode for very high efficiency at light load, or a forced PWM mode. The pros and cons, as mentioned before, the power safe mode gives high efficiency at light load, while the forced PWM mode, of course, gives a very low output ripple in light load mode. So you can toggle between these through the mode pin. We have multiple versions of this family here. Some of them have, for example, a latched off over voltage protection at the output, where we see that users building notebooks and similar applications ask for this specifically latched off version, but this is just one of the many versions that we have with this family. Important maybe is also that these new families is produced on our large wafers, so 300 millimeter wafer in our newest technology that is called LBC9 technology, which is basically a linear BiCMOS technology of the 9th generation. And you can get it in 3 different package options. You can see it's a 1 by 2 millimeter SON package or QFN package, as well as a leaded package, the SOT583 package, and will also be available as a module. Module means with integrated inductor. So let's have a look now at the measurement that we did. You can see here the switch node. And the switch node, when you look at those, you often see a ringing, and that is something that you probably do not want, because this can generate noise in your system. But for this family, on the left-hand side, we have something with an input voltage of 3.3 volt, and on the right-hand side, we have something with an input of 5 volt. But you see here really the 5 volt input is minimal, but basically for the 3.3 volt input, there is no ringing here. And this is because of the chip design that where we have a controlled gate driver and the integrated input filter capacitors. When you compare this to many other buck converters on the market, you really see that this is a very, very low noise performance ringing here, so, or no ringing. So I think this is one of the reasons why we then see here on the next page the measurement that we did on the EMI. And just to tell you, this is not on a specific EMI optimized specific board, but this is just on our standard evaluation module, evaluation board. So the board that you can get from Texas Instruments will show you this kind of performance, and this can help you then, of course, to get your certifications very easily. It can save you maybe a couple of weeks of iterations on your power design, and of course can help you to reduce the cost of the development as well. Now, the other thing, as I mentioned at the beginning, load transients performance. Now, when we talk about power supply for core supplies of system on chip, or of an ASIC or MCU or processor, very often the need from this load is to have a very fast transient response. And here we have showing you the comparator response time to load transients. And this is a very, very small. If you follow here the arrow of the, pointing to this change here you see that there is a very, very small, short response time comparator, and that allows for a very fast reaction time. In this case, we are coming from pulsed frequency mode, so low power mode, from about 100 milliamp going up to 2 amp. And you see here the inductor current rising and falling is very quickly offering a very fast transient response at a very small undershoot. So this is something, again, a very positive effect of the chip design we have done specifically for this family to support also the core supply requirement of many of the digital systems, digital loads. And the next one is here showing then the transient response from PWM mode. So before it was coming from a pulsed frequency mode, and this one here is coming from a forced PWM mode, again from 100 milliamp to 2 amp. And the inductor current that you can see here, pointing by the arrows, rising or falling very quickly, offering a very fast transient response, is despite the fact that this is coming from a forced PWM mode, where typically is in older products here, we can see a much slower response rate. So for both versions coming from pulse frequency mode or from the forced PWM mode, we see a very, very fast transient response to support the core supply requirements. Now, this of course helps us to, enlarge our portfolio here, the same table than before, but in addition now for low EMI, specifically the family that is again pin to pin compatible from 1 amp to 4 amp, and the modules will come a little bit later here this year. Now, the last point for today I want to make is that we have here, as I said before, multiple package options. We have the SON and the SOT, and the module is coming. But the good thing is that the SON and the SOT package can be used to do a so-called dual layout. So looking back at the last 2-3 years, I think many of you have seen that having a very good availability and supply security is very important. And with this one here, you can make your layout the way that you can choose not only between 1 amp, 2 amp, 3 and 4 amp, but you can also change from one package to the other without changing the layout. All of these have a 0.5 millimeter pitch between the pins. So I think that is very important in cases where you need to be sure that you get the supply availability, and as well without changing layouts from multiple output currents in your system. So I think this is something that can help you a lot. To help you, what we have done here, you can find these products on ti.com with the product folder. So there you can find the data sheet, and you can ask for the samples with a link that is shown here. We have also multiple evaluation boards, the EVMs. So depending if you prefer the SOT package or the QFN package, then different kind of evaluation boards are available. Or if you prefer the one with the overvoltage protection latched version, then there's another evaluation board available. And of course, last but not least, as a design tool, you may know our WebBench Designer. So you can start simulating with the WebEng Designer already now before you look at the hardware already. And that concludes my presentation for today. Thank you very much for attending, and I hope it was helpful for you. Thank you.
All right, it looks like we actually had some questions come through the chat. Omar, I think you are better suited than I am to help read them out loud and answer.
Yes, thank you, Kelly. So there was a question about the meaning of point of load, and point of load basically mean that for a general purpose load, we call the device powering that a point of load. So it's not a specific type of load, it's any load. It can be I/O, and it can be anything else. And it's called point of load because we place the device basically at that load. So that is the meaning of that. There was a correction on one of the slides. So when we referred to the EMI, so that is basically 10 to 25 dB. So that was also some clarification to be done there. And there was another question about frequency wobble. So I think the question is about if we have a split spectrum in the device where we are switching slightly at different frequencies to reduce the peaks that we have the EMI at. And Skittles, so this product here does not have that specifically, but we have other products like TPS 62810 or 8503. These two parts have that feature among other devices we have. So the techniques we used in Skittles here did not include split spectrum because Skittles is not inherently a fixed frequency device. It uses a constant T-on time control mode. So these are the questions. And there was another question here about transient response. So the question was, is this fast transient response causing power loss or damage to a component? So with any strong transient in the load on the device, the Vn of our device will have a dip because the amount of energy needed to support that load is significantly increased in a very short time. And usually if the board is designed in a way where the input source of energy is as close as possible to us in the power tree, or there's enough input caps, this dip should not affect the performance of the device. So as long as the energy available at the point of load to support that transient, there should not be any power loss or damage to any component. So Kelly, these are the questions I got in the chat.
Okay, wonderful. And thank you both. And thank you to everyone who joined us today. Today's session will be available on demand on ti.com/MPU, where you can also view a full list of both our upcoming and on-demand MPU webinars. Be sure to join us for next week's MPU topic, Affordable and Reliable CC330X Simple Link Wi-Fi 6 and Bluetooth LE Companion ICs, by registering on ti.com/MPU. Thank you everyone again, and see you next week.